Hey, grade 8, so we have a new chapter. We're gonna jump right into scientific notation because it has something to do with exponents, so we're gonna combine these two chapters together. So, if you haven't watched When Will I Use This in Real Life video, I talked a little bit about scientific notation and how it is used. So it looks like this on the screen here. This is our standard form. Standard form is just the numbers that you usually see every single day, or in the past math classes, right? But now I'm introducing a scientific notation here, and they kind of look the same, right? There's a pattern here. So there's something in the front, and then there's a multiplication sign, and then so it's like a number times 10 to the power of something. Okay, that's interesting. So above here, this is 4,500,000, and they rewrite that to scientific notation as 4.5 times 10 to the power of 6. And on the bottom here, it says 0.00453, and then they rewrite it to scientific notation, and the coefficient here, the numbers in the front, are actually equal. The only difference is that the exponent for the 10 here, base 10, is -3. So interesting. Keep that thought, okay? So we're going to talk about that more. So what's the purpose of scientific notation? Scientific notation is for mathematicians, for scientists, so that they don't have to write all the zeros. As you guys can see, this saved a lot of ink, right? We got a lot of zeros here, and can you imagine every time you measure something, you write all the zeros? If you miss 1 0, that could mess a lot of things, right? So imagine this, you have 5 zeros here, so that's 4.5 million. If I lose one of these zeros, that becomes 450,000. You lost a lot of money. If it were money, that's a lot of money to be lost, right? So scientific notation saves money, saves time. It's amazing. So usually people use scientific notation for really big numbers or really small numbers. Anything with lots of zeros. That's why we use scientific notation. So it could be measuring the distance between planets, between the stars in the galaxy. Or it could be measuring the length of a flea, or the length of a flea's leg, or the weight of an atom, anything that's really, really small. We could use scientific notation. And again, this is the form of scientific notation. We have a coefficient, we have a base of 10, we have an exponent, and we have that multiplication sign in the middle. So there's actually a rule. For the coefficient should be between 1 and 10. It could be 1, but it could not be 10. It has to be less than 10. So you can say 1 to 10, it could be 1, but it cannot be 10. It could be 8.99. It could be 9.9999. It's up to you. And then the power, and then times 10 to the power of something. The exponent there, it has to be an integer. It cannot be a fraction. It cannot be a decimal. It has to be an integer. An integer, again, is any whole number. It could be positive or negative. Okay? Alright, so let's jump in here. It says, tell whether each number is written correctly in scientific notation. If it is incorrectly written, state the reason. So I want you guys to pull out a scrap paper and start saying, is this correct or no? And then tell me why. Okay, so for the first one, it says a horse chestnut has a diameter of about 2 times 10 to the power of 0 centimeters. So if you want to go back to the top here, the coefficient is between 1 and 10, check, times 10 to the power of 0. the exponent 0 is an integer, in other words, a whole number, check. So this is yes, correct. Okay. Alright, so let's look at B here. It says Neptune is about 4.488 times 10 to the power of 9th kilometers from the sun. Again, coefficient is between 1 and 10. The times 10 to the power of 9. 9 is an integer. And that is correct as well. Ooh, let's see C here. It says the approximate wavelength of infrared light is 0.01 times 10 to the power of negative 5 meter. So right away you can see that the coefficient here, it is not between 1 and 10. That is less than 1. And then times 10 to the power of negative 5. This is okay. Both of these are good, but then again, so this one is no. Coefficient is less than 1. Okay. Alright, for D here, it says a football field excluding end zones is 10 times 10 to the power of 1 yards long. Okay, and right away you can already tell coefficient again. Coefficient is this time is greater than 0 or equal to 10. I mean, because it says it has to be 1 or anything above 1 but below 10. Okay, including 1 but excluding 10. So coefficient is equal to 10 times 10, 10 to the power of 1 is okay. That was our problem. Right. Not bad, right? So let's jump into the other examples. Now I want you guys to rewrite from standard form to scientific notation. We're going to go over the first one here together. So it says 427.7. Let's rewrite that in scientific notation. Okay, again, I'm going to give you a reminder. The coefficient is supposed to be between 1 and 10. It is including 1 but excluding 10. And n here has to be an integer, or a whole number which is positive or negative. Alright. So 427.7, this is what we're going to do. This is equal to 427.7, which is 42.77 times 10 to the power of, we went to the left, so it's going to go up. So why did I do that? So think about it this way. 42.77 times 10 is equal to 427.7. Because when I multiply by 10, you guys should remember this, you move the decimal to the right. Okay? So that is why. Alright. So right now, this is not in scientific notation because the coefficient is above 10. So let's move the decimal one more time to the left here. Okay. So it becomes 4.277. Since we moved it to the left once, we're going to increase the exponent to become 2. Again, this is the same thing as saying 4.277 times 100. So we're multiplying it by 100, which means I need to move it twice to the right, which is good. It's equal to that. Alright. So we should check this one here. This is less than 10 and above 1, so that's good. Multiply by 10 to the power of 2, that's good, so that's it. That's how you rewrite into scientific notation. Alright, so go ahead and try B there. Okay. So this one, this time, this is a It's a small number. It's below 1, right? Okay, so our goal is to move this decimal 1, 2, 3, 3 times to the right, so that it will be 7.0, or just 7 if you want. Okay. Again, if you move something, if you change something in math, you need to do something else, right? Since we moved it to the right, and it has to be in the form of times 10, the exponent, is it gonna be 3 because we moved it 3 times to the left, to the right, I mean. Is it gonna be 3? Let's check. So 7 times 10 to the power of 3 is the same thing as 7 times 1, 2, 3. 7 times 1,000, that's 7,000. That's not equal. So that means it is not to the power of positive 3, right? It's going to be to the power of negative 3. 10 to the power of negative 3, you guys remember this from last chapter. 7 is the same thing as 7 times. You flip it, right? It's 1 over 10 to the power of 3. In other words, 7 times 1 over 1,000, which is correct. There you go. So that's another reason why we had to go over the exponent law, so that you guys can rewrite these standard forms to scientific notation. Okay? Alright, so let's do the other way. So what if I give you scientific notation and I want you to do it, to rewrite it in standard form? And this is pretty easy. So 7.1 times 10 to the power of 3, you can do two things. You can expand the 10 to the power of 3. 10 to the power of 3 means the zeros. There are 3 of the zeros. Okay? And then you can just move the decimal 3 times. 1, 2, 3. So that is 7,100. Okay? So this is when you're unsure if what to do, like what to do with the decimal. But this should be easy, you guys. Turning something scientific to standard form. The exponent will tell you if it's positive exponent, decimal place goes to the right. So positive goes right. But then if it were negative, like above here, 7 times 10 to the power of negative 3, negative exponent, as you might have guessed it, the decimal goes left. So it would be 1, 2, 3. There you go. This is pretty easy. But if you forget which one's which, you can always expand. Always expand. Okay? Alright. Okay, so we're gonna compare numbers in scientific notation. So you guys have like a new language here, a new kind of number. So how can we compare them? Alright, so A here, they say 5.6 times 10 to the power of 2 and 2.1 times 10 to the power of 3. If you were to only compare the coefficients, you can say 5.6 times 10 to the power of 2 is greater. But they have different exponents for their base 10. Alright, so here is 2 and this is 3. So the first thing that you can do is this. You can just expand both. Again, a positive exponent means you need to move that how many times to the right. So 1, 2. So 560. And then 2.1, move that 3 times to the right. 1, 2, 3. So that is 2,100. And this is pretty obvious that the 2,100 is greater. So you can just circle this. Okay, so that's one way. Another way, if you just notice this, the coefficients, they're both are between 1 and 10, right? Doesn't matter, one is 7, the other one is 3, but the coefficients, the exponents here, this one has a bigger exponent. So automatically this one wins, right? That one's much greater. Let's go to B here. For B here, the exponents are equal. So all you have to do now is just to compare the coefficients. So obviously this one is greater. So yeah. So that's my advice for you. When comparing numbers in scientific notation, look at the exponents first. If the exponents, if the one is greater than the other, pick the one that's greater. And then if they're the same exponents, then you can compare coefficients. Alright, last but not least, potatoes. It says compare a number in standard form with a number in scientific notation. In 2000, Americans consume an average of 47.2 pounds of potatoes and 5.936 times 10 to the power of 2 pounds of dairy products per person. Oh, that's a lot. Did Americans consume more potatoes or dairy products? Ooh, now we're comparing. Okay, they're comparing 47.2 pounds and 5.936 times 10 to the power of 2. You have two choices. You either turn both of these numbers to standard form, or you can turn them to scientific notation. I'm going to turn them to scientific notation. This one's set, but I'm going to turn 47.2. Let's do that with me. So again, the coefficient has to be between 1 and 10 times 10 to the power of, we move the decimal to the left. That means the exponent will increase. Okay, you can check by, 4.72 times 10, that's 47.2, check. Alright, so again, like what I said, compare exponents first. So obviously, in this case, this one wins because the exponent here is bigger. And let me prove that to you by turning these numbers into standard form. So 5.936 times 100 is you are moving the decimal twice to the right. So that becomes 593.6, and there you go, this still wins. Alright, so we have some awesome activities in class, and I'll see you guys there. Bye guys.